we have learned that if we have a function from f in the complex plane, oops, to the complex plane, and it's one-time differentiable, that's a very special property. So we learned that this is, if we have a function which is holomorphic on omega, i.e. f prime exists everywhere, on omega, this is a very special property. In particular, this implies that angles are preserved, right? So it's the most vivid thing was that if we drew these grid lines here in the reference domain, then in the image under f, they can be distorted in some way, lots of possible ways, but the angles, which is not how I'm drawing it, the angles where these lines will cross will be preserved. They will still be 90 degrees. This is meant to be 90 degrees, which is a very weird thing to happen, a very weirdly restrictive property. However, we can build non-trivial mappings of this kind. And let's start with just some sort of warm-up on this with the very simplest function. So suppose we have f of z is just equal to zeta times z for some zeta belonging to the complex numbers. Yeah. Then what does this say? So let's write zeta as let's choose a number w e to the I phi, as we can put it in polar form. Then let's write z. In general, we're going to write z as the variable in polar form like this. Okay. Then, what is f of z? It's the multiplication of these two numbers, e to the I theta plus this. Yeah. So what's that map doing? That is taking whatever we have here in the reference. So this is the reference domain, right? If we put a smiley face around 0 like this, what is this map doing? It's going to shrink or stretch the smiley face, depending on these numbers right here. Yeah? So if w is less than 1, it's going to shrink it. If w is bigger than 1, it's going to expand it, right? And it's going to rotate it by this angle of phi, right? Given by this thing. So it's going to rotate it to something like this. So I'm drawing it as if it's being stretched. So in this picture, we have w bigger than 1, and we are rotating by an angle of phi like this. Okay, this is what it does. This is the simplest mapping we can think of. And that's what it does. Yeah. So it is just rotating and dilating things. Yeah. It's the same as a linear mapping, where the gradient of the linear mapping is a conformal matrix. Yeah. Okay. So that's super simple. Let's take something a little bit less simple. Let's do g of z equals z squared. Let's see what that does. Well, we're going to write this in polar form, so we have e to the I theta. What did it do? It sends it to r squared e to the I times 2 theta. Right? So let's see what it does to a half circle. So if we have a half circle like this, okay, what does it do? This half circle is going to get wrapped around like this. Okay, And if this is r, then the radius of this guy here is r squared. And every point in here, whatever angle it has, the angle gets multiplied by 2. So this thing over here gets mapped over here, right? And we end up having this half circle mapped all the way around to a circle. Yeah? Everybody with me? Hopefully you've always seen this kind of stuff before. Yeah? So in particular, if we take the entire circle, so this is the reference, and this is the image. If we take the entire circle, this, under this guy right here, then if this is radius r, then it gets mapped to this thing with radius r squared, but we are wrapping around twice, right? So this upper half gets mapped all the way around, right? And then this lower half right here gets mapped all the way around again. Yeah? So we are wrapping twice around the plane. Let me see if I can make a model of this. So if you take a piece of paper and make a slit, you can imagine it like this. Create something like this. Something like this, okay? It's wrapping around twice, but it's not lifting up, it's flat, right? So if you can imagine a rubber sheet where we just make a cut, and we're gonna make the cut where are we gonna make the cut? Yeah, let's make the cut here. And imagine a rubber sheet where we stretch this thing all the way around, laying it flat. So we pull this all the way around, laying it flat. And with that other part, we stretch and pull it all the way around again and stick it on like this, okay? That's what this mapping z goes to z squared does. So it's quite a complicated mapping compared to what we know of x goes to x squared just in a real line. This is more subtle behavior, right? What other examples of complex mappings do we have? Well, one of the homework exercises you have is to show these elementary differentiation rules, which I'll follow. So, given f and g that are holomorphic at z, then the following is true. So if we take the derivative of f plus g, then it is this. If we take the derivative of f times g, then it is this. If we take the derivative of some complex number, let's call it zeta times f, then we can just pull it out. And if we take the derivative of f over g, this is f prime g minus f g prime over g squared, okay? Whenever or if g of z is not equal to 0. Yeah? So, from the fact that we can differentiate sums, products, quotients, scalar multiples, when I say scalar, I mean complex scalar multiples, we have a whole bunch of other functions. In fact, we have all polynomial functions. So, all complex polynomials are holomorphic. Oops. In the entire complex numbers, and even rational functions f of z, which is p of z over q of z, hello, whenever q of z is not equal to 0. So we have a huge number of non-trivial functions, right? We've already seen that z to the k produces quite a non-trivial thing on the complex plane. And if we make a complex polynomial, then you can imagine the very different kind of wrapping around type phenomena we can create, right? So there are many of these things. There are many holomorphic mappings. There are many, many ways to create such things. You know? And that is nevertheless quite a narrow class, just the ones I've listed over here. A way to get even more of them is to consider power series. So, power series. So what do we know about power series already? So all the algebraic rules from this real analysis make sense. So many of the things you know from real analysis were just true for complex analysis, because we can just step by step do exactly the same thing line by line and have the same proof. So for example, if we consider something like this, so let's define the partial sum like this, the sum from k equals 0 up to n of z to the k. Then if we take z times Sn, then what do we have? That's the sum from k equals 1 to n plus 1 of like this, right? So if we go and ask ourselves what this is, then we have this massive cancellation when we take this and subtract this, right? The only survivors will be when k equals 0, which will be this thing, and then we'll have minus z to the n plus 1, right? Which means that Sn, when we factor out the Sn, will be this. It'll be 1 minus z to the n plus 1 over 1 minus z, right? Let's write it like this, 1 over z minus z to the n plus 1 over 1 minus z. No? So if the absolute value of mod z is less than 1, then we can see that this thing is going to converge, because this term right here will tend down to 0. We'll have that the limit as n goes to infinity Sn equals 1 over 1 minus z. So we have learned that this makes sense. This is a meaningful, well-defined function, right? So the function is well-defined. In the ball of radius 1 around 0. Yeah? Okay. Do we know it's a holomorphic mapping? Based on what I've told you. Do we know it's a holomorphic mapping?
Yes.
Why?
Because it's 1 divided by 1 minus z, so it's rational.
Okay. Yeah. In this case, indeed, yes, because it's 1 divided by 1 minus c, yeah, which is rational, except when z is equal, except when c equals 1, where it's not defined, so it's differentiable in time, the unit ball. So in this case, yeah, this guy is a holomorphic mapping. But if we want to consider a more general power series, a more general power series like this, the sum k equals 0 to infinity ak z to the k, where ak are a sequence of complex numbers, we have to think about it. We have to get some idea about this. This isn't necessarily so easy. So, what I'm going to present is a theorem. So, given a series, power series I should say, maybe more accurate, given sequence AK, there exists some R which is inside the interval 0 to infinity. So it could either be infinity and it could also be 0, such that the following is true. If mod z is less than R, then power series sum k equals 0 to infinity ak c to the k converges, and this R looks a bit like k. If mod z is bigger than R, then the power series k equals 1 or 0 to infinity ak set to the k diverges and is defined by the following. One over R is equal to the lim sup as k tends to infinity of the kth root of 1 over k. Okay? So, this is so-called Hallamart's formula for the radius of convergence. You saw this in Calc 2, at least the statement of it, and you saw it in the, well, you saw it when this thing was replaced by a limit, and you were taught this as the nth root test, right? But now we're gonna prove this, and it's not hard to prove. Okay, so proof. Oops. So let's let L be this lim sup as k tends to infinity of the kth root of this thing, right? So R is equal to 1 over L, yeah? Then if we have that mod z is less than R, which is less than 1 over L, then there exists some epsilon bigger than 0 such that mod z is actually less than 1 minus epsilon over L, right? Because if we less than this number, then we can make this number a little bit smaller and we're still less than this, right? Because it's a strict equality. No? All right, so if we therefore look at the remainder, let's not look at the remainder, let's look at the terms from some big N to some big M. So take large oops, totally wrong spelled. Large. Let's have m, which is bigger than n integers. And let's look at these terms. The sum from k equals capital N plus 1 to m of these things here. A, k, z to the k. Yeah? So if we take this stuff and we take the absolute value through, as we can do, this equality, this is a to the k, I'm writing k bigger now. Mod z to the k, yeah. And what's this? This is less than this, so this is the sum. K equals n plus 1 to n mod k like this. And then this thing I'm going to replace by 1 minus epsilon to the L, like this. And we are taking it to the power k, like this. Yeah? Cool. And then from this definition here, so note, we know that L is always bigger than equal to this thing, right? Because that's the lim sup of this thing, right? So we can take the kth powers on both sides. Yeah? So I can put this into star. This for all k. So putting this into star, what do we have? We have that star is less than or equal to the sum from k equals capital N plus 1 to m. And using this inequality now, we're going to have L to the k. This thing is 1 minus epsilon to the k. And let's put L to the k here, and you see what's happening. The L to the k vanishes. So this is just the sum from k equals capital N plus 1 to m of 1 minus epsilon to the k. And this thing is something that converges, right? Because we know that 1 minus epsilon to the power k, this infinite sum converges because obviously 1 minus epsilon is less than 1. So this thing, which is the tail end of it, well, actually, let me just write it like this. In case that's convincing, let's just do this. This is the remainder of the series, right? And since we know that the partial sums of this series, the sum of 1 minus epsilon to the k, sum from k equals 0 to infinity, since we know this converges, the partial sums converge, right? Which means this thing, which is the remainder term, will go down to 0. You see what I mean? Yeah? Give me oral feedback, because I can't hear you. Okay. So this tends to 0 as n tends to infinity, right? And recall we took any m which was bigger than n, right? So in particular, that means that if we take the partial sums, so let's write the partial sums, so define SP to be the sum from k equals 0 up to p of ak z to the p, z to the k. Then this expression over here is just, call this thing star star. Then star star is just the difference between the Sn partial sum minus the Sm partial sum. Yep. So what we've just shown is that these things, the Sn partial sums, is a Cauchy sequence. For any fixed z where z has absolute value less than r, which is 1 over L. Yeah? So Sn is a Cauchy sequence, and therefore has a limit, and therefore we can define this infinite sum, k equals 0 to infinity, a to the k, z to the k, to be the limit of this Cauchy sequence, which exists. This is a meaningful thing, it exists. We've just shown that for every z whose absolute value is less than r, we have a Cauchy sequence, we have a meaningful convergence of this power series. Everybody with me?
Yeah.
Yeah? Cool, so that's one half of this, yeah? The other half, if, on the other hand, we have mod z is bigger than r, like this, yeah? Which again is 1 over L. Then, again, for some small epsilon, we have that mod z is going to be bigger than 1 plus epsilon over L. Right? Since it's bigger than this number, we can make this number a little bit bigger and it's still going to be bigger. Yeah? So there must be some tiny epsilon for which this is true. Yeah?
Mm-hmm.
Cool. So let's take a subsequence that achieves this limit here. So let Kn be such that the limit as n goes to infinity of this 1 over Kn is equal to L. For sure there is such a subsequence because it's defined as the lim sup. We can certainly find a subsequence that creates this. Yeah? Then what happens? Well, we're going to consider these terms like this. So let's, for this subsequence, if we look at this thing, a to the Kn times, let's take the absolute value of everything, mod z to the Kn. Well, what do we know? Well, we know that this thing here is bigger than this. So this is, and this guy here is getting closer and closer to L, right? So in particular, we can find some large enough n such that this thing is bigger than 1 minus epsilon over 2 times L. So let me actually write that. I can just launch straight into this. So put in the steps. So there exists some n0 such that a Kn 1 over Kn is bigger than 1 minus epsilon over 2 times L for all n bigger than n0, just by definition. Yeah? Cool. So take n to be bigger than this particular n0 and then look at these terms. So let's take the absolute value of a Kn, z to the Kn, absolute value, that is a Kn, absolute value of z to the kn, and then we're going to use what we have. So then this thing is bigger than 1 minus epsilon over 2 times L, everything to the power kn, just from this inequality over here, right? And this thing here is bigger than this, 1 plus epsilon over L to the kn. Yeah? So I'm running out of space. I'm going to put this up here. Let me erase a little bit of space. So this stuff, like this, is bigger than, so we're going to have the L to the kn and the 1 over L to the kn are going to cancel. So this is going to be 1 plus epsilon. Give ourselves more space. This is going to be 1 epsilon over 2 to the kn. Still not enough space, times 1 plus epsilon to the kn, right? So let's take the power kn outside of everything. We're just multiplying this stuff all together. What are we going to have? We are going to have, we're going to have 1 plus epsilon over 2, and then minus epsilon squared over 2. Is that right? We have 1. This will give us minus epsilon over 2. This is plus epsilon over 2. Yeah, no, that's right. So the kn. Everybody with me here? Speak up. Tell me if you're with me. Everybody say something.
Yeah.
Everybody good. Okay. And then this number right here, for small enough epsilon, is indeed bigger than 1, right? Because this is 1 plus epsilon over 2 minus epsilon squared over 2, right? Yeah? So this thing tends to infinity as kn tends to infinity. Everybody good? So what this means is that if we have some z which is bigger than this r, then the terms will actually go to infinity. Right? The absolute value of the terms of the series go to infinity, so there's no possible way that we can create a convergent series out of them, right? Yeah. So that proves the theorem. All right. Theorem. So, given power series the sum from k equals 0 to infinity, ak z to the k, as before we let r be defined by this Hadamard formula. One over r is equal to the lim sup as k tends to infinity of the kth root of ak. Okay. Then f of z, so since it's now we know it's defined inside this ball like this, this is a well-defined complex valued function from a ball in the complex plane, right? Then this thing is holomorphic in this ball of radius 0, okay? Sorry, ball of radius r around 0, and the derivative is given by this thing, exactly what happens when we differentiate this term by term. Okay. in this thing. So implicit in this is the statement that this thing will actually converge inside the same radius of convergence. Yeah? And this is indeed the derivative of what happens if we just differentiate this term by term just as if it's a polynomial. Okay, that is our claim. All right, proof. Couple things to note before we get going. So this is extremely powerful, the first thing to note, because what this says is that we can treat these guys just as if they're polynomials, and it's a general thing about why power series are so powerful, that inside the radius of convergence, all the nice things you can do with polynomials you can do with power series. They behave just as well. In particular, differentiation, you learned in Calc 2, you can also integrate them term by term if you're doing power series in the real line. So this is extremely a powerful theorem. So the theorem I'm about to prove will work also for just real valued power series on the real line, and that, one of the consequences of that, for example, is that we can replace many of our integration methods that we learn in Calc 2 just with the fact that we can represent many functions as a power series and then integrate them term by term, right? So a big chunk of Calc 2, we learn all these complicated integration methods, the trig integrals, trig subintegral, integration by parts, U subs, whole bunch of stuff, right? There's a kind of like toolbox of integration methods, and once you have a power series, integration is just easy. You can just integrate it term by term. So this is an extremely powerful theorem, and it's also quite surprising that you can have this infinite sum, have it be meaningful, and have it behave just as nicely as a polynomial in lots of ways. And we're only going to talk about the differentiation because complex integration will come on to later, and that's a different story altogether. But this is quite an important and powerful result, and kind of a surprising result. So let's launch into this. So how are we going to do this? We are going to have a number of limits in play, right? So we're going to pick some large n, we're going to decide on later. Okay, and we're going to take the partial sum Sn of z be the sum from k equals 0 up to n of ak z to the k, so that's just the polynomial, and we're going to let ek of z be what is left, right, from the partial sum, so that's the remainder terms. Okay, and our task is to show that the differentiation is exactly this expression, right? So let's let g of z be this power series. Actually, the first thing I should do is show that this thing converges in the same radius. Okay, so let's do that as a little aside in the corner. Okay, so in the corner, we're going to show that this thing here has the same radius of convergence as this guy, right? And to do that, all we need to do is show that if we take the Hallamat formula for these coefficients right here, that it gives us the same result, right? And so in particular, what we want to know is that, that the limit as k tends to infinity of the kth root of this expression here is the same as this thing. right? Because if we knew that, I should take a lim sup. Yeah, let's take the lim sup. Because if we knew that, then what is the radius of convergence? This r, it is defined by 1 over this thing, right? And it's going to be the same number if we have that this is true. Yep. So this is implied by having that k to the 1 over k, or the limit of this thing, tends towards 1. If we can show that, then the statement above makes sense. Does everybody agree? Speak up, people. Do you agree?
Yeah, I agree.
Okay, thank you. What about everybody else?
Yes. Yeah, we do. Yes.
All right, good. So what we need, therefore, is to show that this is true. All right? To show this is true. All right, give me a suggestion. How would we do that? How would we show this? Where is this kind of stuff familiar to you? Where have you seen this before? Okay, what if I do this? What if I write this? This is implied by the limit as x goes to infinity of x 1 over x equals 1. Right? That's definitely true. If this limit is this, right, then the special case of the limit when we just go over the integers as k goes to infinity has also to be equal to 1. Yeah? So now the question is this. How would we do this? We're going to use L'Hopital's rule, and we're going to use logarithms. Because what we're going to do, we're going to say, okay, let's f of x be x to the 1 over x, right? And then we want to find out this limit as x goes to infinity, and this is a trick that you for sure have seen many times. Whenever you have a function to the power of another function, we're going to take a log of it, right? So we're going to have that this is the same as f of x is equal to e log of this expression right here, right? Log of x to the 1 over x, like this. So we only have to understand this limit, and then we stick it in to e. E is continuous, so we have no problems with that, right? So if we understand this limit as x tends to infinity, which is just this, then we're all set, yeah? Because this is just composing a continuous function to get f, right? We're composing continuous function e with this thing to get f. So the limit of this thing is, sorry, the limit of f is the limit of this thing applied to e, just by composition of continuous functions. Yeah? Everybody with me? Oral feedback, people?
Yeah.
Yeah? All right, good. Look at this. Tell me what you think the limit is. We could use L'Hopital, or we could just look at it. If we just look at it, what do we think the limit of this is? You think 0? Tell me why. Yeah, log is our slowest growing function, right? Log grows incredibly slowly, right? Log grows slower than any root power of x, no matter how small a root we take, or bigger root, whichever way we describe it, right? So log divided by x is absolute massacre. This log is going so much more slowly to infinity than x. This thing is indeed 0. So then when we pass to the limit, put it over here, the limit as x tends to infinity of f of x, because of continuity of this thing, is equal to the limit as x tends to infinity of this thing. You probably can't read because off the edge of the board, but this is just e to the 0, which is therefore just 1. Yeah? So we have that this, which is this, does indeed have a limit equal to 1. Yeah? So we have what we need. So this has got limit 1, which implies that this limit is the same as this limit. So this thing will indeed converge inside the same radius of ball as we started with. Everybody good?
Mm-hmm.
So G is well defined. in the ball of radius r. So I'm going to make this convention of when I'm going to do a lot of balls centered on 0, and I'm not always going to write bracket 0. So when it's just ball subscript r, it just means ball of radius 0. And that's a common notation you'll see in many math papers, that you use ball centered on 0 so often you stop writing like this, you just write it like this, okay? But if you ever forget what I'm talking about when I write B subscript capital R or little r, just stop me and I'll tell you, okay? So this is well defined in this, okay? Good, so what are we going to do? Well, we've got to try and show that as we take the limit, as we take the derivative of this thing, we're going to write in quotient form, it's got to tend to our function g. So this is what we want to show. We want to show that f of z plus h minus f of z over h minus g, we want to show that this thing is small, right? And we're going to do that by breaking stuff up. So we're going to replace f as the partial sum plus the error, okay? And then replace this by this. Yeah, and then, okay, this is what we're going to do. We're going to write, this is less than Sn of z plus h minus Sn of z over h minus Sn prime of z. So Sn is just a polynomial, so for sure for small enough h, for some fixed n, we can make this thing small. And then this thing, the next thing I'm going to have Sn prime of z minus, let me put a z here as well, g of z. We want to show that this thing is small. And finally, we want to show that this thing is small. Okay, let's make sure everything works, right? So what are we doing? We're writing f as the sum of these two things, right? So then this entire quotient is this quotient plus this quotient. Yeah? And then we're going to put this s prime in here, and then have it here, and then minus g. So do you see from the triangle inequality that this thing is less than equal to the sum of these three terms? Speak up, people. Everybody give me a verbal signal that you're with me.
Yeah.
Okay.
Yeah?
Yeah.
Okay, good. So that's our job. We want to control each of these three things, and we've taken some large n. I haven't specified what it is yet, okay? And we are going to first choose the n to make this thing small and make this thing small. And once we've chosen the n and fixed the n, we're going to choose the h to make this thing small. That's our strategy. Okay? So more formally, what we should have done is say let epsilon bigger than 0, and I claim we're going to be able to find an n to make this thing less than epsilon for all sufficiently small h. In fact, all I will need is that this thing is still inside the ball, and I'll be able to show that this thing is less than epsilon. Okay. So then, having done that and chosen that n to make this thing small and this thing small, n will be fixed, and then I have the right to play with this thing for our fixed n and make this thing small. And that may allow me to conclude that this thing is less than 3 times epsilon. That's the way we're going to do this. Yeah? That's the strategy. Okay? Cool. And we have to deal with each one of these guys in turn. This guy is the guy we're going to start with. This guy right here, let's call that guy A. So let's estimate A to begin with. So we assume that Z plus H is inside the ball, because otherwise this this thing f of Z plus H doesn't even make sense, right? It's not even defined, right? And we estimate A. So let W equal Z plus H. Yeah? And then what are the terms of this guy like? Well, we have the coefficients in front, and then it's going to be Z plus H to some K minus the same coefficient on this guy, Z to the K. So what I mean is each individual term will be like, let me write this in words, so each term of A will be something like AK, let's use our notation, W to the K minus Z to the K, like this, right? Well, I mean, divide by H then. Divide by H. Yeah, that's each term of this thing, right? So we want to try and estimate W to the K, Z to the K. So here's an algebraic identity. I'm sure you've seen that if we do W minus Z, let's write W to the K minus 1, W to the K minus 2 times Z, W to the 1, and then this here is Z to the K minus 2, and then the final term is Z to the K minus 1. All right, so I claim that this thing this is a comma right here, is equal to just W to the K minus Z to the K. That's my claim. And why is that true? Well, if we multiply through the W, right, we have W to the K, then we're going to have W to the K minus 1 times Z all the way through, right? And then if we multiply through by this guy, we're going to have Z W to K minus 1, and then all the way through, and we'll have a massacre. There'll be a massive amount of cancellation. There will only be 2 survivors when we multiply this thing through. That's my claim. How many of you have seen this before? This is how we show that, this is how we show the power law. Differentiation of d by dx to the power n is n x to the n minus 1 before doing implicit differentiation. How many of you have seen this before? So what happens? So we're going to have W to the K, multiplying through with W first of all, W to the K minus 1, Z, blah, blah, blah. And the final term will be W to the Z, K minus 1 over here. And now we multiply through with the minus C right here. So the minus Z, we're going to have this term, minus Z, W to the K minus 1, and so on, blah, 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 blah. And when we multiply minus Z with this term, we're going to have minus W Z to the K minus 1, and then the final term will be minus Z to the K. Yep. And then we see the massacre occur, right? So this kills this kills this, and all of these terms on the top are killed by the guys underneath. So the only 2 survivors of the massacre are this and this, right? Those are the only 2 survivors. Cool. So that's our identity. Yeah? So in particular, if we consider Z plus H, now I'm switching back from W to Z plus H to the K minus Z to the K, then W minus Z is just H itself, right? Over H. Then this thing is less than all of these terms here, right? Yeah. So we take the absolute value of this thing it's less than the sum of all of these terms right here. So I'm running out of space, so hoping that this is clear. So it's less than the absolute value of all of these terms. Do you see what I mean, people? Speak up. Oral feedback. Okay, so let's look in more detail. So let's look at this expression. If we divide through like this, yeah, then w minus z is just equal to h, yeah? Yeah? And this thing for sure is this, yeah? Yeah? So then if I take absolute value of this thing, it's just going to be absolute value of stuff in the box. And what else do we know? We know that this thing, which is w, is inside the ball of radius r, and so is z, of course. So all of these things, when we take the absolute value, will be just less than r to the power k minus 1, right? Because this guy, absolute value is less than r to the k minus 1. This will be less than r to the k minus 2 times r, right? All the way through. Yeah? Yeah?
Yeah.
How many of these terms do we have in this red box?
K.
K. Yeah, we have k. You just count the number of terms which have w. We have w to k minus 1, blah, 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 all the way down to w to the power 1. So there's k minus 1 terms in w, and then another one. So there's k terms in total. So this stuff means that this thing is going to be less than k times r to the k minus 1. Yeah? Cool. Let's start from exactly this point. So I'll try and put this video up, and let's remember we start exactly from this point of estimating this guy, and we'll do that on Tuesday. All right, have a good day, people. I will see you all on Thursday. Bye-bye.